All right. Well, it's a pleasure to introduce you to Martin and Ben. Guys, take it away. Thank you.
Okay, thank you. So I'm Martin Johns. This is Ben Stock. This is joint work with our colleague Sebastian Lekies. He's not here, so he got the biggest picture on the slide. We work at SAP. Currently, Ben is in Microsoft. Sebastian is currently at Google. But what we will present today is something that we did together a while ago at SAP. And we also have a joint blog called kittenpigs.org. And so if you're interested in the final slides of this talk or need more information on what we're doing, feel free to visit us there. So what will we be presenting in this hour? This research is embedded in a bigger project in which we investigate or continue to investigate this in the current state of cross-site scripting. And we did a large-scale on DOM-based cross-site scripting study there, and Ben will tell you about this a little bit. And part of the study was then for us to check what are the current countermeasures against cross-site scripting. And one of the things that we investigated are client-side cross-site scripting filters. And after we saw how they worked, and we are security researchers, next thing that we were investigating is, okay, how can we bypass them? And so the second half of the talk will be mainly our insight in how to bypass current state of client-side cross-site scripting filtering. But before we can talk about bypassing cross-site scripting filters, we have to talk about two technical things. For one, we have to talk about cross-site scripting. Given the nature of this conference and also that you choose to come to this talk, I kind of assume that you know pretty much everything about cross-site scripting already. So we'll go through this very, very quickly. But then also we have to talk about a little bit how does cross-site scripting filtering on the client-side work. And so this will also take a little bit of our attention. But first, talk about cross-site scripting. So when you talk about client-side web security, there's mainly one question that you want to answer, or that is in your mind. And this is when I'm accessing an untrusted website, maybe attacker.org, how can it be that attacker.org is not able to access any of the sensible resources on an unrelated website, for example, gmail.com? And the answer to this question is the same origin policy. The same origin policy restricts all active content, JavaScript or other things that run on the website, to resources that are part of the same origin, part of the same domain. And hence, attacker.org is not able to read your Gmail. How do we get around the same origin policy? The main way of getting around this is called cross-site scripting. In the context of this talk, you only have to remember that cross-site scripting is a code injection vulnerability that allows the attacker to run JavaScript code under the origin of the attacked web page or on the vulnerable web page. Hence, if in this case Gmail would have a cross-site scripting vulnerability, which more or less is a way of the attacker to inject HTML and JavaScript into the Gmail application, he is able to execute JavaScript under the origin of Gmail, and the attacker is allowed to read your Gmails. So what can we do with cross-site scripting if we are an attacker? So the main thing that we will see today is you can open an alert box. So this is a good proof of concept, but it's not very convincing in respect to security. But what you actually can do with cross-site scripting is quite a bit. You can do session hijacking, as you're pretty much aware of already. You can alter arbitrary content in the web application that is displayed on the client browser. You can steal passwords from the password manager of the browser. And what it boils down to, a successful cross-site scripting attacker can do pretty much everything with the web application that you can do yourself. But he is able to do it under your identity and your account. So in respect to your account, a successful cross-site scripting exploit is more or less a full compromise. If you look into the literature or into related research, there's a classification of cross-site scripting, and the classification usually talks about two big classes. It talks about reflected cross-site scripting, which is very, very common, and stored cross-site scripting, which exists but is much harder to find. Cross-site scripting filtering is only concerned with reflected cross-site scripting. So we won't talk about stored cross-site scripting at all because it's out of scope for the client-side filters, and therefore there's nothing to bypass for us anyway. And therefore, let's have a quick look how reflected cross-site scripting, what reflected cross-site scripting is. Reflected cross-site scripting is a vulnerability in which the web application blindly accepts attack payload from the malicious person and incorporates it in the corresponding HTTP response on the corresponding HTML. So you have, for example, a URL containing cross-site scripting attack. This URL is then server-side or client-side processed, and the payload that you can see in red here is then part of the HTTP response and interpreted by the web browser in a context which then leads to JavaScript execution. We will come back to this slide later on when we talk about how to stop this. But now, for now, only what you should take away here is what can we do against cross-site scripting? So if you're the owner of the application, if you're the operator, if you're the programmer, you have various things that you could do to combat cross-site scripting. You could actually program securely. You could try to escape all the attacker-provided data. You can try to be careful and not allow code injection vulnerabilities. You can also try to use secure frameworks. Some of them work good, some of them work not so good, so your mileage may vary. And you can leverage modern browser features, something like the content security policy or sandboxed iframes to make your application much more secure to use. If you're the user of the web application, there's not so much that you can do. So you have kind of rely on the ability of the operators of the application that they are able to combat cross-site scripting. And as we will see in a second, they are not that good in that. You could turn off JavaScript, but I think 95% of all modern web pages simply stop working. Or you could hope that the current client-side cross-site scripting filters that are deployed with Internet Explorer or Chrome, or that are provided by the NoScript plugin, help you. And this will be, again, the second half of the talk. So now, hand over to Ben.
Okay, so before we actually go into talking about how a cross-site scripting filter works, I want to tell you a little bit about work we did last year for CCS in kind of basically finding a lot of different real-world vulnerabilities that are in the wild, and specifically DOM XSS vulnerabilities. So in order to find those, and we wanted to kind of find those at scale and in a fully automated way. So obviously you can see a certain piece of code and then try to look at what it might be doing and how it might process your input and try to figure out if there's a way that you can inject your own code. But we were more of the dynamic analysis guys here. So what we did is we basically patched Google Chrome, or Chromium, which is the open source version, to employ taint tracking, meaning that for each character in a string that is inside the JavaScript engine or the WebKit rendering engine, and it's Blink actually, we attach a taint byte, basically, sorry, a taint byte, sorry, yeah. So for each character we can specifically say, this is coming from the URL, this might be coming from the referrer, or this might be benign code. That would be benign stuff that was hard-coded into the website. We paired this with a Chrome extension that allowed us to kind of automatically crawl a large number of websites, and also kind of as a user interface, which I will be showing you in a second. And in doing so, we kind of generated these large numbers of flows. So we see, for example, there's a call to document write, and we see exactly, as I will show you in a second, which parts are benign, which parts are attacker controlled. And using this information, we actually built a fully automated exploit generator, taking this information and then trying to generate a valid exploit, and which was then afterwards also validated by our extension again. So before I kind of talk more to you about this dry part, I'm just going to show you a small demo. So this is it's just an advertisement, and the advertisement is also one of those things that are often vulnerable to DOM-based cross-site scripting. And if I reload this page right here, this is basically, so this is our taint Chrome. I see this flow down here. It's a tainted flow to document write. And in this case, to kind of have a nice presentation, I put everything that is user-controlled in black. And if you look at the URL, I think it's very small up here, but basically this is Blackhat 2014 is coming from the URL, and it ends up down there in this partner value of the iframe source. Okay, so in order to kind of from this point try to see if we can exploit it, and this is obviously only doing it manually, the first thing I want to do to now execute a cross-site scripting attack is to go ahead and try to break out of that existing iframe and kind of write a script tag that will at some point trigger the vulnerability. So let's first do this here. So I kind of only added the quote and the closing brackets. And you can see down here the fact that kind of actually this is now the end of the iframe. And there's some stuff in the middle. If you're aware of HTML parsing rules, you know that everything that is between an opening iframe tag and a closing iframe tag is only displayed when the browser does not support framing. In this case, obviously, yeah, Chrome supports framing. So let's do the following so that you can actually see that there's something happening here. So let's close that iframe as well. And now you see down here, this is basically, this part was what was originally embedded by the website. And we kind of, with our payload that I showed you up here in the URL, I kind of went ahead and closed the iframe. So at this point, I could go ahead and just say, okay, I now want to script alert 1. No, actually, let's not use alert 1. Alert 1 is boring. So this is a very cat-related talk. So let's call cat. Let's see what happens. Oh, nothing happened. So this is where the XSS auditor comes into play. This is a very straightforward attack where the whole script is kind of up there in the URL, so it's easy for the filter to detect. Nevertheless, this still constitutes a vulnerability because we got to that point where the JavaScript engine would have been invoked with this call to cat. So in order to show you that I'm not lying about this actually being a vulnerability, I have the second window here of Chrome, which I started with the XSS auditor off, which is basically a command line flag. And let's see what happens. So we have a successful cat attack. And now have a different cat that is being shown. And obviously, as Martin said it before, basically having an alert box open, or in this case showing a cat picture, is just arbitrary JavaScript code that we are able to execute. All right. Okay, so now we know, using this information and using these precise precise taint bytes, plus the knowledge of JavaScript syntax as well as HTML syntax, we were able to kind of automatically generate a large number of exploits and exploit 1 or 2 sites. Actually, it wasn't just 1 or 2 sites, so we ran that on the Alexa top 5000. We did find many cats, XSS. Actually on 480 out of those domains, which kind of boils down to being roughly 10%, which was a huge surprise to us. I have to admit, we didn't think that it was that bad. And for recent work, and also this is what we are going to talk about in the rest of this presentation, we then later did it as a little bit larger scale, kind of looking at Alexa top 10,000, but the numbers pretty much align. So it's 9.6% up there, and it's 9.58% for the second set of things we called. And in these cases, all over those domains, you can see that we found roughly 1,600 unique vulnerabilities. I could spend like 15 minutes just talking about how we determine uniqueness, so I'm going to skip that part right now. If you want to know more about it, find me later. And in order to validate that this is actually a vulnerability, we said, okay, regardless of the fact that the auditor might actually block such an exploit, it's still a vulnerability on the server side, or in the client side code, sorry. Just the fact that the auditor blocks it doesn't mean that it's not a vulnerability. So these numbers are actually coming from the auditor being turned off. So at this point, this was basically kind of the beginning of this year. We had this large set of real-world XSS vulnerabilities. And our testing platform was built into Chromium. And as you saw, the XSS auditor is also part of Chromium. And then we figured, okay, why not try to find out how well the Chrome XSS auditor actually protects us from these kinds of vulnerabilities. So what we did is basically took all of the exploits we had validated beforehand and then reran them with the auditor enabled. And big surprise, the auditor didn't catch all of the vulnerabilities. And that's actually motivated the work we are presenting right here. So we said, okay, so why were some of the exploits going through and others weren't going through? So let's have a look at the source code actually. And can we in this kind of try to determine whether we can actually increase the number of bypasses of the auditor. Okay, Martin?
Yeah, good. So we were sitting on this big pile of real-world cross-site scriptings, of which some were caught by the auditor, and some weren't caught. And as Ben already said, so we got a little bit itchy and said, okay, we can do better than this. So let's go to the bottom of this. How much of this exploit can be modified by modifying the payload, by modifying the injection vector that we use? so that the auditor won't catch it. And and the nice thing about the auditor is there's a rather good paper written by Adam Barth and other people that give details on how the auditor works, so the design philosophy, and it's open source. So we sat down and read the code, and the auditor itself is not that much code, but every single line of the auditor code is very significant in respect to its functionality. And so while it wasn't very complex, it took quite some time to go through this. But but you need to understand this very, very well. So to build your bypasser, we needed to this. But let's first take a step back and look how client-side cross-site scripting filtering works in general, because all three client-side cross-site scripting filters that currently exist more or less share the same functionality. They all combat reflected cross-site scripting. Therefore, I come back to the slide that you already seen, where we showed what reflected cross-site scripting is. And if you look closely, I think you can already see this. The attack vector and the executed code that is the cross-site scripting vulnerability are both present both in the response and the request. So you can, in this case, in the URL, you can see that in the URL, the script alert 1, and in the same script alert 1 appears in the corresponding HTML of the corresponding HTTP response. And this is that allows for a very simple matching algorithm in theory. In theory, it's very, very simple finding reflected cross-site scripting. Look at the URL, look at your HTML. If you have the same thing in the URL and in the HTML, tada, cross-site scripting. Shouldn't be so hard. The XSS auditor, which we at least, or which is widely considered to be the most advanced and state-of-the-art in respect to client-side cross-site scripting filtering, wasn't the first. The first client-side cross-site scripting mitigation was provided by the NoScript plugin, which is in some reason, on some matters, a little bit simpler than the other ones because it only looks at the requests. So the NoScript is a very security-centric plugin. You can also say it's very paranoid. Therefore, everything that it looks a little bit like JavaScript in the request is considered to be an attack. And therefore, it stops everything that might be insecure, which is good for us security people because we are also very paranoid. So I think all of you probably are running NoScript. But it's not something that my mother could use because then there would be this, for every false positive, she would be completely lost. Internet Explorer was the first mainstream browser to adopt cross-site scripting filtering, and they apply the methodology that I have here. So they look at the outgoing requests, they do some magic, they're building some regular expressions that then are applied to the incoming HTTP response before the response is passed, and trying to figure out if there are matches between the URL, in this case, and the HTTP response, and then this might be a cross-site scripting problem. It's a very capable thing. It's completely lost or mostly lost when it comes to DOM-based cross-site scripting, so this is a weakness of the Internet Explorer. And also, this is done before the HTML is passed. Therefore, it might miss some occasions where JavaScript is executed because they don't replicate the whole HTML parsing in the filter, they just approximate it. And also they might be susceptible to obfuscation attacks, for example, and like this. The cross-site scripting auditor said, okay, look, so the people that built the cross-site scripting auditor looked how IE is doing this and said, okay, we can do this better, right? And so they don't look they don't look at the request at all at the beginning. And they also don't really look at the responses. The XSS auditor is part of the HTML parser. And what the HTML parser does is every time it encounters JavaScript or something that might lead to a JavaScript execution, only then it looks into the outgoing the corresponding request. So we go now into this a little bit deeper and do a step-by-step overview how the XSS auditor works. So, as I told you, the XSS auditor is part of the parsing process. So the incoming HTTP response is passed by the HTTP parser. And every time the HTML parser is encountering a construct, so this might be either an HTML tag or a certain HTML attributes that could potentially lead to JavaScript execution, the auditor is invoked. And then, if certain conditions are true, the auditor tries to find tries to find the JavaScript that you just saw in the request. So these conditions are important. You have to remember them because they are one of the keys to building the bypasses. So the first condition is the auditor only does the matching process, so the looking for the JavaScript in the request, if the HTML construct that executes JavaScript is encountered in the first the initial parsing process. So you get the HTTP response, and then you pass everything that's in the HTML response, all the HTML. There might be more HTML coming into the page using something like inner HTML, outer HTML, things like that, that also invoke the HTML parser. These so-called document fragments don't invoke the cross-site scripting filter. The reason for this is performance, because for certain web applications, something like Gmail, you have many assignments to inner HTML. And there, because all the browsers currently are in this performance war, every single bit of performance is important, and therefore for inner HTML, for example, the XSS auditor is not invoked. The other important fact that you have to remember is the matching process, so the looking into the URL, if there might be the attack payload and that is currently executed, only happens if in the URL or in the post body for HTTP post requests, if in the URL in this case are certain dangerous characters are included. So the philosophy behind this is for the vast majority of all cross-site scripting attacks, you need at least one of the following characters to be able to do your injection, because you always have to break out a certain syntactic context to create your JavaScript context that is executed. And more specifically, these four dangerous characters are the opening and closing. What are they called in English? You know, the greater sign and lesser sign, and the double quotes and single quotes. And if you don't have greater or lesser signs, double quotes or single quotes in the URL, the next step, this step, is not invoked. If these two conditions are met, so if the auditor says both, okay, here's a JavaScript carrying construct, and the preconditions for a potential injection are present, then the auditor does the matching process. So it takes the JavaScript that you just found during the parsing process and checks for this JavaScript in the URL and for post requests in the post body. And there's the third important fact that you have to remember, and I will go into this deeper because, again, this is some of the functionality that allows us to build the bypasses. Depending on which of the nature or the type of this HTML construct, so if it's a tag, if it's attribute or something else, the specific matching rules are different, and we will need this. So, and then if we have the situation that we found a JavaScript, the invocation criteria have been met, and we found a matching part of the URL, for example, that contains this JavaScript, the auditor concludes, okay, this is an active, successful cross-site scripting exploit, and therefore the JavaScript is removed during the parsing. So the JavaScript parser itself never sees the injected JavaScript, which worked because, as you saw, Ben's initial exploit didn't go through. So it's capable tool. So let's quickly go 3 slides over the matching rules, because as I told you, they differ for the various JavaScript contexts, and they're also basis for some of the bypasses. So the most basic injection is injection of complete script tags. So you inject script tag, you inject your JavaScript payload, and sometimes you even close the script tag, or actually in most cases you have to close this. If such a script tag, if any script tag is found during the parsing process, the corresponding matching rule is that the auditor checks if the content of the script is contained in the request. So the script tags themselves are not, the auditor doesn't look for script tags in the request because they're mandatory for injection anyway, and only looks for the JavaScript code itself. It skips initial comments and white spaces. This is normalization step, which makes sense. And it only checks up the first 100 characters because they are significant enough for identifying if there's a match or if there's not a match. And it checks up to 100 characters, but it might terminate earlier. So the matching process terminates if certain terminating characters are met. And the most important terminating character in this context is double slashes for the comments, because this is usual technique that you use for certain injections where you end your injection vector with JavaScript comments. The second matching rule is for HTML attributes. So you might have, there are two classes of HTML attributes that can carry JavaScript. For one, you have the event handlers, something like on error, on load, on something. And you have attributes that carry URLs, because there's the JavaScript column pseudo URL scheme, which causes the browser to execute JavaScript directly. So all source and href attributes and all on error and other event handler attributes invoke the auditor. And for all these attributes, the auditor checks, and here's the difference, if the attribute either contains a JavaScript URL, so in this case, the JavaScript URL itself is looked or checked in the request, or the event handler. And the matching rule is that the complete attribute has to be contained in the request. So with text, we had that only the JavaScript code has to be contained in the request. For attributes, it is that also the attribute name, and in this case, the equal sign and the quotes and stuff like that, has to be contained in the request. So it looks, if you have an onload alert 1, the auditor will match against the URL, in this case, also the string onload alert 1. The third matching rule is for HTML elements that can load active content over the network, something like script tags with a source attribute, which then creates an HTTP request that gets the JavaScript from a remote server. Or the same is for embed, an object, an applet, all the text that then load plugin data from other servers. In this case, the matching rule is that both the tag name, in this case a script or object, has to be in the URL, and also the full complete attribute with attribute name and attribute value has to be used. So this is the hardest, the most strict matching rule because of, I think, has false positives. So to sum up, if you look now on a bird's eye view, the auditor works in 3 steps. There's the invocation phase, in which the auditor is invoked if the 3 conditions that we talked about are met. Then there's the matching phase, depending on which the HTML construct is that we're looking for. And then if we have a match, there's the blocking phase. Coming from here, it's rather obvious how to build your bypasses, because they're in this 3-step process. There are 2 steps that are interesting. So you can either try to build a bypass that avoids the invocation steps. So you build a payload that somehow executes JavaScript without meeting one of the conditions that need to be present that the XSS auditor gets real active. Or otherwise, you try to fool the string matching, because this is what it boils down to. So for them, this is the reason why I showed you the string the matching rules, and so specifically. There, at one point, the auditor has to find an equal string both in the HTML and in the request. And if we are able to create an injection payload that somehow fools this matching process, we again win if we would be the attackers. Okay, and so now Ben will take you through, I think, 4 demos, if I counted correctly, where we exemplify a couple of those bypasses that we found. We found more, but at one point, demo gets a little bit tedious. And so if you're more interested, we documented all the bypass classes in the white paper that should be available, I think, over the website. So, but no, here's Ben.
All right. So as Martin just said, there are kind of 2 different ways to get by the auditor. So you can either try to avoid the invocation, or you can try to pull the string matching. So now I'm going to talk first about how to kind of make the auditor not even actually do anything, because you kind of don't meet the criteria that it needs. So the first and foremost, and also quite an obvious one, is actually using eval. So in our work, we found that quite some vulnerabilities are actually triggered by kind of user data that is then used in an eval, which is obviously not a good thing, but I mean it was good for us because we found a lot of vulnerabilities. And the problem here is obviously in this case, as you can see on the right-hand side, this is something that only happens in the JavaScript space. So it never actually goes to the HTML parser, and thus, since the auditor is part of the HTML parser, it can never actually see this payload. So that's why it only works for injected HTML and not for injected JavaScript. So to kind of show off our prototype once again, I have this other thing here. So this is basically just a demo. So these vulnerabilities, or these things that we're showing to you here, are actually not something that we kind of came up with, but this is kind of stuff that we saw out there in the wild, which is kind of, it makes you think about what things are wrong with the web. And please excuse these underscores. They're just to highlight the fact that this is actually injected. There's a formatting error, so actually the whole URL is actually injected, so it's not just the HTTP. Sorry for that. Nevertheless, so there's something that we saw in the wild where there was a function that was basically called after, and this was with set timeout, basically a function that traced whether the user was still there or not, and it was passed the URL of the currently loaded page as the first parameter. And as we can see here in this example, we see that, so we have this visited 1 second, and then the argument is actually completely tainted, which is basically the URL that you see up there. So again, we can now just try and have a look if we can break this or not. Oh, sorry. Like this. So what we see right now is the fact that the flow has changed slightly. Yeah, you can see that we're still calling visited 1 second, but this time so this is again our injected part that I just changed in the URL. Obviously this leads to a parsing error because so there are like these characters over here that are trailing in this case. So to kind of see that this actually does work, we can do this, but at this point we haven't changed anything, right? So we're still kind of calling the function that we initially were calling. So let's try again and call the function cat, which should hopefully work. All right. So again, we were again able to kind of do our arbitrary payload, put it in here, and the auditor is not aware of that, obviously, as it's not part of the JavaScript engine, but rather the HTML parser. Then, Martin already said it. There are also kind of ways of getting around the invocation inside the HTML parser itself. And first and foremost, as you already said, Google opted to disable the auditor for these document fragments, which is obviously for performance reasons. It makes perfect sense in my mind. However, as we found, there are so many vulnerabilities out there that actually use inner, that kind of have a flaw when they use inner HTML, which allows an attacker to always bypass these things. So that's pretty simple. So we didn't actually have to generate payloads that were targeting to bypass, but rather just, oh, it's an inner HTML flow, so let's exploit that, and so it will always pass through the auditor actually. And the second part is what Martin just also briefly talked about, this so-called unquoted attribute injection. So the auditor is disabled if those 4 characters are not found in the request. But depending on the situation, you might actually have, and we found a lot of that stuff as well out there, you might have situations where the user input, so basically something that's coming from the URL, is written to an attribute without actually using any quotes. That means in order to break out of this attribute, I don't need quotes, so I don't neither you need the single or the double quote, and depending on what kind of attribute it is, so it might be a iframe, for example, where I can then use one of those JavaScript URLs. I don't actually have to break out of that existing tag as well. So I don't need the lesser or greater signs. So there are certain situations where you can kind of get past the auditor because it's just not invoked because of this matching rule. Again, this is, I guess, for performance reasons because Google says the likelihood that you will find a vulnerability that comes out, is able to be executed without these characters is pretty slim. Then are these things that we like to call HTML-free injections. So again, that's something that happens actually in the JavaScript engine, and the HTML parser again is not involved. First and foremost, there are the DOM bindings. So you can access, for example, an existing script tag from JavaScript. You'll get document get element by ID, you get that script tag, and then you say script.source and assign a certain value to it. That kind of changes something in the parsed HTML node. So it's kind of in memory. This changes the source attribute, but it doesn't generate any HTML anymore. So it's not parsed, and that's why it's actually never going to go through the HTML parser. Second thing, we didn't actually kind of try to find vulnerabilities like that. We actually found one vulnerability that we could exploit because it was a second order flow. So you have cookies and you have web storage. Maybe some of you guys know local storage or session storage. It's both kind of the two things. And in these cases, the actual injection vector is not found in the request because the auditor actually looks at the request body and the URL, not the cookies. So if the payload is kind of in the cookie already for some reason, then you can kind of exploit that. And what we actually found was pretty interesting. So we found a flow for which we generated an exploit. And when we initially hit that page, it didn't work. It's like, okay, well, maybe we did something wrong, or maybe they used some filtering. But then we refreshed the page, and all of a sudden there was an alert box popping up, and we were like, okay, what's going on now? And what was actually happening is that this site kind of noted the entry URL. So the first time you hit that domain, it would actually store the URL from which you came, which was in the next step then used inside an eval in an unsecure way. And so kind of the first you had this flow to the cookie, and then once you kind of reloaded that site, it was extracted, this value was extracted from the cookie, and then all of a sudden we had this alert box. But as I said, we didn't kind of target those, but these are definitely vulnerabilities that are also out there. And third, there are also alternative data sources. So there's, with HTML5, there are these post messages that allow you to kind of send messages across domain boundaries, because Martin already said it. Same origin policy is usually in the way of that. But if you can get a reference to another window, you can say window.postMessage, and then you just send one of those messages. Again, this is not something that is actually an HTTP request, but it happens completely inside the browser. So in this case, again, as the auditor is not looking at these things, you can actually find it. All right. So again, to demo these things would be kind of lame because it's super straightforward. So the second part, or the second phase in which we might be able to kind of fool the auditor is issues related to string matching. And yeah, we kind of want to have a situation where the XSS auditor, as we said it, once he encounters for example, a script tag, it looks for the whole content in the URL. So are there situations out there where you actually have your malicious payload, but it's not, so the matching doesn't work? And actually, lucky us, there is. So you have these things, kind of, we like to call partial injections. For example, you can hijack an existing tag or an existing attribute. Think about a script source where there's an assignment. So you have a document write saying script source, and then comes the user input. This is the partial injection. And as Martin said it already, for scripts, actually Chrome looks for not only the attribute's value but also the name. So the name would not be contained in the request, but only the value. So this is obviously a bypass. And then there's like a third way of going about it, and this is what I'm going to show you a small demo. Hijack an existing script node. Okay. So again, let's fire up our taint browser. We see down here a flow, again, to document write. That actually is kind of an assignment of the variable x. In this case, it doesn't do anything, but we didn't want to kind of write a lot of code that would fill up the console. So in these cases, it's pretty similar to this eval case that we saw earlier. Again, we could be able to do the following. So what usually you would try and do is break out of that existing tag, regardless of what kind of tag it is. So in this case, it's a script tag. So let's try that and see what happens. So yeah, we get an unexpected token. That is okay. Yeah, that is. And now let's try and do this one. Script alert 1. I hope it won't work. So yeah. Again, the XSS auditor refused to execute that script because, as you can see up here, it's completely contained in the request. So, but why should we actually go ahead and try to to do it in such a complicated way. If we can just go ahead and finish the assignment here. Let me just get that down here again. So close the string with a single quote, do semicolon to kind of end that statement as a whole. Then we call cat. We don't call alert1. And then if I do this would actually fail because you can see it up here. They're actually unexpected tokens, so that they're not there. And as Martin said it already, we can use // which is basically the JavaScript command, and this is what you see a lot of times in XSS payloads. And if I hit that again, it says again, get attack successful. And the problem here is, if we look at what we just saw in terms of the flows. So we had this partial HTML, which is actually called something different, but nevertheless, so you had the sum value and then you had the call to cat. And so this is actually, so the lower part is actually what's being parsed by the HTML parser. And Martin said it, that the double slashes actually end kind of the matching. So the auditor looks for at most 100 characters, or if at some point they encounter a double slash, that's kind of where they end their matching. But the problem is, in this case, that although our payload up here also ends with double slashes, we actually don't have this var x assignment up here. So this is why the string matching obviously doesn't work, because as it's looking at the whole source of the script, it cannot find it in the request. Then something that is kind of similar is a class we call trailing content. So the idea here is to kind of use existing content that is out there in that page to fool the auditors. So you kind of inject something, but there's more stuff behind that. And so the key is you want to be able to kind of have a payload that will be executed. So you don't want to have a parsing error, but again, you don't want to be found as well. So let's look at another demo here. So this is just also something very, very small. You would think that this is kind of made up, but no way. There are actually people that kind of use this to get the size of a div or something. What we can see here is the fact that we're inside this style, and so let's try and break out of that style for now. Oh, sorry. Oh, come on. All right. So we can actually see that this worked out perfectly. So what we're going to do now is kind of, again, as usual, we want to call our function cat. And so let's try that. Image source equals .com, which should not resolve, I hope. No, let's call r.foo. All right. So let's try the following first. Again, the XSS auditor says, no way. I found an error handler, so this on error. I hope you can see it up here. It's pretty. Let me just get that here. All right. So the auditor kind of sees, okay, there's an on error, and while it's parsing, it finds it completely inside the URL. So this is okay. No, we're not going to execute that. But if we look a little closer, we can actually see that if you see up here, you have this px and a single quote and a closing tag. So why should we not just go ahead and kind of make use of that? So what we do is we call cat, and then we just use a semicolon, which basically in JavaScript takes kind of separates what is it? Not attributes. What is it? So two phases of the execution. So basically the next line of code in this case. And so again, the target for us is to generate a payload that will be executed that is valid JavaScript, that will not cause a parsing error. We don't really care about runtime errors after our payload has been executed. So let's go ahead and do that. What we can actually see is, again, we have the cat. So why do we have the cat? We have this on error here. And this is, so basically the red part is what is also contained in the URL. So first we have this call to cat, and then we have just a statement that says px. Actually, you can see down here, there's an uncaught reference error because px is not defined. But we really don't care because our payload has been executed already. So this is kind of interesting if you find these situations, and there are a lot of those out there. So again, let's briefly recap. So this is what's actually happening. We have this image source down here that the auditor now finds an on-error handler. It looks for the on-error handler, both the name and the value in the complete URL, in the URL. Tough luck, px is not contained in the URL, so in this case, again, we can kind of bypass the auditor. Similar to that, there is a class we call trailing slash. So if we find an injection that is followed by a single slash, in order to kind of generate a payload that is still valid, and we want to, so the idea is always to comment out the rest that is behind your actual payload. So what you need to do in these cases is just inject one single slash, because the other one is already there, and then Chrome will again look at the request, find one slash, not both, and since it goes up until the point where both slashes are already done, that's kind of why it doesn't work. And similar to that, there is trailing SVG. There's actually something in the anime tag of SVG where you can kind of separate these statements. If you have a semicolon, it only executes the first part, and then it's similar to this slash. But as Martin already said it, we refer you to the white paper for a more detailed explanation of how that worked. Okay, so now for the actually most fun part, I think, of the injections we found in total. What we like to call double injections. So double injections, we have 3 different classes. So let's say we have a single input, so maybe the URL, but we have multiple injections. It means that it's written several times, at least twice in this case. That's why it's called double injections. And you have these situations where you have a single input, say a part of the URL, that is written inside one sink, so one document write call just takes part of the URL once and another part of the same part of the URL twice, for a second time, sorry. You might also have multiple inputs with multiple injections, so basically taking 2 different parts of the URL and putting them in there. And you might actually even have multiple injection points with multiple sinks, but this is way too complicated, I think. So I'm gonna try and demo only the single input multi-injection. Okay, so let's look what we see here. So in the URL, we have a parameter called height. And this parameter called height actually ends up in this is a very constructed case, I have to admit, in this assignment to height of this image. So the kind of the normal blunt way of going about this would be to try and close the image tag, which we don't need to close, and then do that. Which, again, obviously, script alert 1 is completely contained in the URL, so this is not going to execute. So the question is now, but as we see, we can kind of inject it as such, as a whole, but we know that the values are actually used at 2 different points, so in the string. So the idea of what we're doing here is to kind of put the script, the code that we want to be executed in this part that we control completely. But why should we actually not go ahead and try and do that otherwise? So let's do the following. What happened if we kind of exchange this closing script tag with an opening script tag? So let's just do that for now and see what happens. Okay. Ooh, unexpected identifier. What's up with that? So if we take a closer look, you see that this is the image, which is closed. Then we have a closing script tag that does nothing, basically, because we haven't had an open one. And then we see an opening script tag, but then comes the unexpected identifier, namely the single slash, the single quote, I'm sorry. So is there a way of kind of going around this? And you might have guessed so already. There is. So what I want to do here, there is a function in JavaScript called void, which takes a parameter and, as you might have guessed already, does nothing. So let's try and start, just bear with me here, just start this call to void and let's see what happens. Okay, so we still get an unexpected token here, but we can kind of see that, so we have an opening call to void here, then everything that comes until the next closing script tag, which is here, would be executed as the JavaScript, but obviously this is not syntactically correct JavaScript. So why can't we just see where we were at behind that part? So we see again this closing script tag, which is, if you look at the URL, which is up here. So why don't we just try and do the following? Let's see if that works. Okay, so now what do we have? We have right here in the middle a call with this opening script tag that calls void, and then we have a closing script. And we had a lot of stuff before that and behind that, which is kind of causes the page to look weird, as you can see here. Just this little piece here. But what happens if I actually go ahead and instead of just calling void, no, we don't want to call that. Let's call cat. Ooh, cat picture. So what we did here is basically, we were not trying to kind of inject our vector such that it is in the UL at a certain point or in consecutive order, but rather, since we know that the value is actually going to be used twice, we can just kind of turn the script tags around, and this is kind of what you see here. So this is actually, in red I've kind of marked this, the payload we have here. And so this is what it initially looks like, right? You have this image height, and then it's kind of broken. But if we go ahead and kind of reformat that to show what is actually being kind of given to the JavaScript engine, you actually see the following. This is exactly the same code I showed you before, just I changed the line breaks slightly. So again, we have the call to cat, we have the call to void here, which is basically ended by the end here. So to kind of summarize that, we actually take that part behind there, which is this call to cat and the call to void, and then since we know that the other part is going to be injected in there as well, once again, we can just take this from here. And as you can probably imagine, this would be very hard to find with string matching, because what the auditor actually looks for is this. And this is not contained in the UL at all. So there is no way that this could actually ever be caught by the auditor. Okay, so now I've talked to you about those bypasses that we found and kind of showed you how we were able to exploit it. And then we went ahead and kind of, having gathered this knowledge that we, on kind of, there were this set of vulnerabilities, and there was this knowledge we had about the auditor's internal workings. So we kind of went ahead, and since we're from academia, we do empirical studies all the time. So we used our existing infrastructure. We had these 1,600 unique vulnerabilities on 958 domains. And we kind of took our existing exploit generator, which I didn't show you here because it would be way too complex in this case. We kind of took that and added a few if conditionals here and there to kind of enable us to use these vulnerabilities we found. And actually, we were not targeting the DOM bindings that I was talking about earlier. We were not targeting second order flows, and we were not targeting these alternative attacks such as post message. But still, on 776 of those domains that we had exploits on, we could, out of the 958 domains we had exploits on, we could successfully exploit still 776. Never mind about the domain count here. Obviously, if you build a sum on that, it would be way more than 1,000. But that is actually because we have, let me say it. So it's actually more than these 776. But as I told you before, we had multiple vulnerabilities. On average, like 2 vulnerabilities per site. So we could kind of exploit domains using inner HTML and eval. That's why they're up there twice. So as you can see here, these were the results we found in the real world top Alexa 10K, which kind of leads me now to the conclusion. So what should you take away? So cross-site scripting is still a big problem, especially with DOM-based cross-site scripting, which appears to be not that well understood compared to reflected XSS, so server-side reflected XSS. And we found DOM XSS on about 10% of the Alexa top 10K. Browsers do deploy countermeasures, and Chrome arguably has the best filter out there, and there are several publications that also kind of make that point. But the security analysis of the auditor has shown that there are many bypasses, which kind of are both related to invocation of the auditor and as well as string matching issues that I just discussed with you. And what else to take away? So we built, for previous work, a fully automated system that allows us to find DOM XSS at scale, which is a cool thing. We then enhanced our generator to kind of target these known issues that we found in this work, allowing us to even exploit more stuff even with the auditor active. And we evaluated the impact of these issues, and we found that in total we could bypass 81% of the auditor on 81% of the domains that had vulnerabilities, in 73% of all vulnerabilities in total. All right, and with that, I'd like to thank you very much for your attention, and I'm happy to cover any questions.